Well, it's a great pleasure and privilege to be starting off this series. So I hope this starts it in the right kind of way. You've heard a little bit about my biography already, but I thought I'd just put it up here because science and religion has been the kind of way I've lived. So I was unimaginative at school. I did maths, physics and chemistry A-levels, but I didn't like any of them sufficiently to do them at university. Wasn't quite sure what to do. My mum had done an evening course in geology, and this is how it happened. She found geology quite interesting, so I said, right, I'll do geology then. So she bought me a copy of Geology Made Simple, which I read on the train to the university interviews, and that's what I did. So I did a geology degree. I did some research towards a PhD in geology, which I didn't finish. That's another story. And then I put in red because it kind of interrupted what looked like a promising scientific progress, a call to ministry, which meant I did a theology degree as part of my ordination training, and then a theology DPhil. So my life has been in both camps, and for a few days each year, I return to being a scientist again when I go with the science students to Anglesey and do some geology for them on their ecology field course. I want to say a little bit about the scientific method. The first thing to note, of course, is that it's been massively successful. And although I'll be speaking about what I think are the limits of the scientific method later, I'm a huge fan of its possibilities and potentialities. One of the easiest ways to measure the significance of science advance is through the use of technology. Well, we've just been, I used to be the owner of a phone. We've just been playing with these. The degree to which, all the elements we needed to make a phone have been lying around in the earth for millions of years. It just took us a while to figure out how to put them together. But our ability through scientific understanding to manipulate the world according to the ways we want it to be, is just incredible. And what about the weather forecast last week? That was amazing, wasn't it? I was walking around on Friday when it was spring-like and warm, and they told me snow was coming on Saturday. Very hard to believe, and yet snow arrived. More impressively than that, they were forecasting the snow more or less a week out from the event. That demonstrates a degree of understanding about the world which is extremely impressive. So how does the scientific method work? Well, here's a potential everyday situation with this couple looking perplexed. We can apply the scientific method to their dilemma. So the first thing you have to do as a scientist is some sort of initial observation. You have to begin with something you've noticed and want to think about. In this case, the fact that the car won't start. The next thing you need to do is to generate some hypotheses as to why the car won't start. So perhaps we might imagine the battery is flat. The next thing you need to do is to devise an experiment. And I put here an experiment as kind of like a very structured and ordered and careful set of observations. But the really key thing about an experiment is you need to be able to test one thing at once. So our experiment is going to test whether the battery is flat or not, but not leave us open to other kinds of possibilities. So we could remove the battery, we could test it with a battery meter, or more simply, if we had a good battery we knew was good, we could just swap it out, put it on the car, and see whether it works. And by doing that, from our experiment, we'd either confirm the original hypothesis, yes, the battery was flat and now the car starts, or else we'd find that we've got a really good battery on the car now, but everything is just as before, and the car still won't start, so we have to go back and generate another hypothesis. I put here in the kind of small parenthesis, confirming the original hypothesis, that is, that it's not false. You hear all the time that science has proved this or science has proved that. Science never proves anything. What it does demonstrate is that the hypothesis is not false or has not yet been falsified. That's a very important distinction. And because science doesn't prove things, that's why, and we'll come back to this, it's so interesting because it's eminently revisable and changeable. Now, in using that, I've simplified the scientific method to its absolute basics, but already there are a whole set of hidden assumptions that exist in that method which we ought to pull out. And the first is what I've called methodological naturalism. That is, we assume that the universe is made up of a closed set of chains of causes and effects without something interrupting. For the purposes of my scientific experiment, Anglican priest as I am, I do not imagine that somebody has cursed my car, and that's why it won't start. Until I can lift the curse, fooling around with the battery is going to do no good whatsoever. If I'm in my scientific head, then methodologically, for the sake of what I'm going to do, I'm going to bracket out any notion of special intervention. I'm only going to think about a chain of cause and effect which I can see and observe and hope to understand. It's really important to remember that word methodological, because at the beginning, many of those who were pioneers of science would have had a religious faith. But what they're doing is they're bracketing that out for the purposes of investigating the world in a particular kind of way. Over the time, it's a lazy assumption somehow that science disproves God because God's not involved in science. It's important to understand that it's a methodological choice. Now, the fact that this methodology yields such extraordinary results ought to give you leave to think about what that says about the nature of God and and God's interaction with the world. But that's not a question for now. The scientific method works best where experience is repeatable and testable. It's very hard to apply the scientific method to a completely unique event. Sometimes science does talk about unique events, such as the meteorite impact at the end of the Cretaceous period, which brought the dinosaurs to an end and allowed for the rise of the mammals and in turn our emerging. And you could say, of course, that's a kind of random chance, unique, odd event which somehow interferes with nice chains of evolutionary cause and effect. But of course, meteorite impacts on planets are extremely common. I mean, just look at the surface of the moon. So although we're applying what looks like an odd, sometimes a sort of uncomfortable explanation for what's happened, because it seems to bring something from beyond into the picture we're analysing, in fact, we're still talking about repeatable experience, which is testable to some degree. Also notice that the science assumes that the world is intelligible. That's a very important hidden assumption, that there's some point in attempting to be rational in understanding. And also that the world exists beyond the subject. Most scientific papers don't begin with a justification that the external world exists. Those sorts of questions are reserved for philosophers. And you have to be careful where you start talking about this kind of thing, for questions of your mental health are raised. But mostly science doesn't get into those kinds of questions. It simply assumes that there's something beyond, there's an objective world beyond the subject. And as far as possible, it seeks to remove subjective bias from its understandings. That, of course, is impossible. We cannot get away from our place in the world. I'll come back to that. But as far as possible, we seek to make sure that the results of science are independent of the person who's engaged in the scientific study. That's why the results should be repeatable and can be confirmed. And I think the best thing about science is that all thinking is revisable. It can be challenged. I'm going to say a bit about human evolution, which I'm very keen on. And there's probably no other field in scientific endeavour where results are being challenged and overturned and new pictures emerging. And that's what makes it exciting. But it also leads to a kind of different notion of what counts as truth to some religious ideas. And I think both challenge each other. The very fact that it's possible to test and revise an idea gives you some degree of confidence that the idea being proposed holds water, because it's done so as part of a whole community of critical fellow engagers. So, I mean, one of the best ways to make your career is to pull somebody else's theory apart. So any theory that survives is going to be good. Whereas in religion, in my religion, a doctrine of the Trinity, once it's there, it's supposed to always be there. And if you call it in question, you could be in trouble. I wanted to give you an example first of the power of scientific explanation from my old field of geology. So here are a few bits of evidence, which I'm going to go through, which in and of themselves were curious and puzzling, and were put together in the 1960s to produce what was then a revolutionary new theory. I'll do this very quickly, I hope, but not too quickly. If we were to strip away all the oceans from the globe, what you find is this extraordinary pattern of deep trenches. There's a particularly deep trench down here, and big ridges in the middle of the ocean. There's this mid-Atlantic ridge here, which crisscross and form an interesting pattern across the globe. What are those ridges and trenches doing? You can find in certain places around the world, particularly around Japan would be an example, you can find this kind of pattern of earthquakes. So this is a plot of distance against depth. And you find this intriguing linear pattern of the foci of earthquakes going down to about 700 kilometres below the surface. What's causing that pattern of earthquakes? They were called Benioff zones before anybody knew what they really meant. Long, long ago, people realised that you could fit the continents back together, and they more or less fit. The black is overlaps, the red is gaps in this little picture. But it's not bad. It's not bad. Why on earth should the continents fit together? This is a fun thing. Polar wandering curves. When rocks solidify, either igneous or sedimentary, if they've got metallic particles in them, those particles can align with the magnetic field of the Earth before they're solidified. So the rocks preserve the orientation of the magnetic pole in the past. So what you can do is you can look at a succession of rocks and see how apparently the direction of the pole has moved. So you end up with these, here's the North American experience and the European experience, and the pole appears to have wandered all over the Earth. What's going on there? Why would that be happening? If you go to the ocean floor, here's an image of the Atlantic Ocean. You find that the ocean floor has these magnetic stripes, positive, negative. We know that the Earth's magnetic field, at the moment, north is north and south is south, but that's not the way it is the whole time. The polar alignments flip through time, and the sediments on the bottom of the ocean record that pattern of flipping. And look how symmetrical the pattern is about the mid-Atlantic ridge. How do you explain that? Or the distribution of past species. Lystosaurus, up here, had a range which included Africa, India and Antarctica. Only if you put the continents back together again does that make any kind of sense, how you could have a continuous range for that particular species. Also, interestingly, between England and Scotland, you find completely different trilobites, now only separated by a few miles. Why would that be? Well, in the 60s, the notion of plate tectonics was proposed by Tuzo Wilson, an American, and Dan Mackenzie, British Cambridge academic. And here's a little model. I don't have time to go into this in huge detail, but the notion is that you've got convection currents in the mantle, in the upper mantle. You've got this very ductile layer here called the asthenosphere, and then you've got a much harder, brittle bit on the top called the lithosphere. Those patterns of earthquakes are caused as one plate of the Earth is what's called subducted down beneath another. And the melting of the sediments on here causes volcanoes to be above, and the movement of this plate against the other causes those earthquakes. It only goes down to about 700 kilometres, because by then it's melted into the mantle. And where this goes down, that causes the trench in the ocean. So you've got upwelling material here, convection current going down here. So here you have what's called a hot spot. You have upwelling material from the upper mantle plating itself on the lithosphere, and the two plates move apart as new material is created and added. And that's what's going on right now as we speak in the middle of the Atlantic Ocean. So that Britain, Europe and America are moving apart at about 5 centimetres a year, something like that. Doesn't quite explain the rising cost of air travel, but could be a factor. So suddenly, one theoretical model seemed to explain a whole set of disparate, puzzling evidence. I think plate tectonics is one of the most beautiful scientific theories to have emerged in the last... It's up there with Darwin and the origin of species, because it's so elegant. So there's no doubt in my mind about the power of scientific explanation. It can pull together a whole set of disparate observations into one coherent notion of what's going on, which, of course, is yet to be... I mean, nobody can see this section. This is an imaginary cross-section. Nobody's tested it. Nobody's gone down on a subduction plate. But there's a whole range of evidence put together, and this is inherently testable as we get better and better observations. So, having talked about the power of scientific method, I want to talk about its limits. One of the things that really intrigues me is where do hypotheses come from? The scientific method in and of itself can't tell you how to generate a hypothesis. There's a kind of gap in the method which relies upon human creativity and inspiration. A eureka moment. So the scientific method, at its very, very heart, has this gap, has this creative, sort of inexplicable thing called inspiration. This is a bit more controversial, but I think I'm prepared to defend this. I'll read it out. Science, by virtue of its method, is essentially not about explanation, but about observation and so description. It's about the discernment of patterns, an extraordinary complex interlocking set of patterns. And question, is it reducible to the form A, as far as we can tell, tends to be associated with B? Now, I've done my uttermost to make science as kind of trivial as possible here. So this is rhetorical. It is rhetorical. But I have a sense that science doesn't actually explain things. What it gives you is a very sophisticated set of observable associations which as yet have not been demonstrated to fail. You can discuss, that's a point for discussion. I'm being provocative there. But if science is anything like that, I think it excludes a whole host of quite important questions, like purpose and meaning. What is the point of life? There's no scientific experiment you can do directed to that question. ethics and values, is murder wrong? I could take a poll of opinion in the room and put up some statistics about it, but what experiment am I going to put together to work out whether murder is wrong? And aesthetics, is this beautiful? So there's a whole set of quite interesting, important elements of human experience which seem to be out of the range of the scientific method. Now, at one extreme, what happened with the logical positivists in the 20s and 30s is they say, well, these questions are just meaningless then. We can't do much with those. In fact, when you say murder is wrong, what I'm really saying is I'm disgusted by murder, or I disapprove it, or I don't like it. There's no way of making a statement that it's wrong. That was one view. It's a view that didn't persist very long. But these seem to be important questions which science can't directly, at least, come to. And I put here, even on the basis of its own spectacular successes, science can't address the question, how do you explain the intelligibility of the world? I think for me that's one of the most intriguing questions. I'm sort of updating Leibniz. Those of you who know Leibniz's question, why is there something rather than nothing? I like that question. But I like better, why is there an intelligible something rather than nothing? Why should the world be explicable? That's gravitation lurking on the slide there. I think the last thing I'm saying about limits is, and this is a really big one, there's no meaning without interpretation. This is Wittgenstein's very famous image. Look at it one way and it's a duck, look at it another way and it's a rabbit, and depending on how you choose to look at it, that's what you see. You cannot escape the process of interpretation when you're trying to make sense of something. And science and scientists are no different. They have to come at questions, developing of hypotheses and theories, with a whole set of assumptions about what they think they might find and expect to find. We can't escape our human location. And as we'll see in human evolution, that's had a big effect, the kind of interpretive framework that people have come with. And I want to use human evolution as an example of science, what I called here, science pressing beyond itself. When we tackle the question of how did we come to be here, it's very hard to escape us. It's very hard to take the subject out of the science, because we seem to be intimately related to the question. We're involved. And I think scientific inquiry at its best spills over into wonder. One of the things I like about Brian Cox and his programs is that he's prepared to allow for those moments to happen. He's not telling you how to feel or interpret that space of wonder, but he is prepared to sit with it and to see it as something which flows out of the science but is not quite belonging to the science. So I suggested here that scientific inquiry can generate questions, or help generate questions, that it cannot necessarily constrain. So, yeah, you notice something, this causes you to wonder, and the wondering leads you to notice new things. There's a very important hermeneutic circle going on there. Okay, a bit of human evolution. These are our nearest living cousins. In the whole of this next bit, you'll be meeting the family. Because, of course, one of the striking things about evolutionary understanding is that every living creature is related to every other. This is a bonobo over here. These are chimpanzees up here. And I'm a bit confused about this because it all depends on how you count it, but it's said that 98% of our DNA is shared with chimpanzees and bonobos. it kind of depends on which bits you're looking at, and sometimes that's a bit, you have to get beneath the surface of those calculations. But nevertheless, the DNA distance between us and them is very little. And if you observe them, I've observed gorillas at the local zoos. That's about as close as I've got. It's kind of uncanny. It's just uncanny, isn't it? Watch the way they hold their young and move and use their hands. So that's our nearest living cousin, and this is us. We do all these clever things, like pushing our territory, albeit very temporarily, off the earth and somewhere else. And even by 32,000 years ago, we were engaged in this in southern France. Extraordinary cave art, which has multiple explanations, but probably is related, at least to some degree, to religious practice and understanding. So here is a family tree. So these are points of common ancestry, and then you break off and you produce another living creature. It's a bit of a cheat, because at the moment, of course, the Australopithecus here and the Homo erectus here are no longer with us. So what we get is a slightly distorted picture. So I said here, putting back the missing rungs of the ladder. So if I stand up on here, so it's against health and safety. At the moment, I blocked that out on my phone. At the moment, the closest we can get is from here to here. And it makes it look like the gap is comfortably big. We're doing quite well over against those bonobos and chimpanzees. But when you fill in part of this process here, you begin to find that our alleged uniqueness as creatures is much less than we could formerly have assumed. So putting back in the missing parts of the ladder of this process, I think is very important for our self-understanding. It says here that the lineage between chimps and us split about 7 million years ago. It might be 6 million years ago, but it's of that kind of order. And it's been said by Van Hoesteen, who's a South African theologian, the story of our species is virtually the story of the growth of the human brain. That's really important, because it used to be thought, and you can still see it on T-shirts, the kind of changing, you start off like this, and then you go up like this, and then the best ones have us like this over the computer again. But we now know that's not the case, really, because one of the earliest and distinctive adaptations was bipedal locomotion. So standing upright and walking happens very early, and much before the generation of a brain like our own. So what happens up here is crucially important in terms of what makes us human beings. So here's some of the family. This is the famous Lucy, Australopithecus afarensis, about 3 million years ago. EQ is encephalization quotient. You can think of it as power to weight ratio. If you have a big engine in a big car, it may only be as fast as a small engine in a small car. So encephalization quotient measures brain size, usually measured in cc's, actually, a bit like engines, against body mass. Because all things being equal, the bigger you are, the bigger the brain. So this gives you a much better sense of what's going on. So an EQ of about 2.5, which is more or less where bonobos and chimps are. They're about 2.3. One of the extraordinary things here is from Latoli in Africa. We have this amazing set of footprints, fossilized footprints, which were formed because there was a succession even of light ash clouds and then rain, which meant that these got fixed and then filled in with ash and preserved. And there's an extensive walkway of maybe 200-300 meters where you can see the footprints and lots of other footprints as well. But you can then test from the impression how the foot was operating. You can see that the big toe is absolutely in line with the other toes. Actually, some people think it's not quite, but it's near. It's as like your foot as almost anything else. And that's brilliant evidence for the assumption of upright walking. But if you were to meet these characters, they're going to essentially be like meeting contemporary chimpanzees, except they're walking and looking much more like you. Homo habilis is held to be the earliest member of Homo, which is kind of our human lineage, about 2.5 to 1.8 million years ago. And you can see the EQ now is up to 3.1. Although there's been some, I should just pause and say, there are two mistakes which paleoanthropologists make regularly. The first is that as soon as they find anything that looks a bit different from anything else, they claim a new species. So we end up with huge numbers of species which may or may not be distinct. That's the first question. Homo habilis might be a victim of that, might not. The other thing they do is as soon as they've found something, they assume that it must be on a direct line that leads to us. So you end up with a whole set of competition about which of the past hominids is actually in our direct line and which were offshoots which ended up in dead ends. Homo habilis is pretty certain. There's a slight doubt whether it's actually part of Homo erectus, who we'll meet later. But in any case, Homo habilis is the first one to be using stone tools. Homo used to be erectus, now it's agaster and erectus. So agaster is held to be the originating form in Africa, and erectus, the slightly developed form, which you see in lots of other parts of the world, including Asia. Homo erectus is the first, this is extraordinarily Homo sapien looking version. But it's the first one of our ancestors, if you dress them up and put them on the tube, might just about pass. Because their physique is very similar. They're about up to 6 feet tall, long-legged, athletic, would have been very efficient and good runners. And they're extraordinarily successful. You see, they go from 1.8 million to 100,000 years ago, roughly. And they were the first species to spread out of Africa and spread all through Asia and right to the Far East. Homo heidelbergensis, we're getting much, much closer to us now. EQ 4.8. Very good evidence that they created and used wooden spears. And there's a brilliant excavation that went on a number of years ago at Boxgrove in Sussex. So these people, these are British, as well as being African, as well as being in lots of other places as well. Here's my favourite one, Homo neanderthalensis. EQ essentially the same as us. In fact, they had, on average, they had bigger brains than you and I do. But then on average they were a bit heavier than us, although shorter, a bit stockier and shorter. But what intrigues me, and this is where you can't escape those assumptions and interpretations, is look at the range of, this used to be the way Neanderthals were safely described, because that makes them very different from us. More recently, especially with the advent of DNA, we now know that many had red hair and pale skin. Other reconstructions start to look much, much more like us. And there are lots of debates about how different were they in terms of the way they used tools, or in terms of the way they used body decoration, or the way they might have had jewellery. It's almost certain now that they were engaged in deliberate burial. that's where the kind of weight of evidence has now swung. It's gone both ways. And the more that we learn about Neanderthals, the more the gap between them and us has reduced. And if you're of European descent, then, like me, you've got something like 2 to 3% Neanderthal in your DNA. And that's only been known for the past 7 or 8 years. The DNA studies are revolutionising this whole area. I thought I'd mention the Denisovans. 2013, a tooth was discovered. Here's the tooth in a cave in Siberia, and a tiny bit of a finger bone. So I put this up for a joke. I googled it, and somebody's come up with some kind of reconstruction. How on earth they've done that from a tooth and a bone, finger bone? I don't know. But the interesting thing about the Denisovans is that we know a lot about them, and we know it all because a complete genome has been created from the fossil record. So this is the new way of doing. You don't need to bother. Send somebody else out of the field, get the DNA, then you can do the real analysis. And if you have East Asian heritage, especially if you come from Melanesia, you would have 6%, or Australian Aborigines, about 6% of the DNA from here. And if you come from other parts of Asia, it may be 2% or so. And they seem to be a population that existed roughly contemporaneously with Neanderthals, but had a different kind of range. So, trying to see if anyone here looks like they might have some Denisovan DNA. We're all a glorious mixture. Had what's called the Hobbit, Homo floresiensis, comes from the island of Flores in Indonesia. When this was first described, I think back in about 2010, it was dated as being 12,000, as recently as 12,000 years ago. We now know it's as recently as 60,000 years ago, which is slightly different. But here is I was going to say a typical Homo sapien, only if you've been working out against the so-called Hobbit. So a complete mystery, really, how they've arrived in Indonesia. And here's a little. Don't believe too much the figures on this. It's just the easiest one I could find, but it shows how modern humans and the Denisovans and the Neanderthals have at various points engaged in interbreeding, all at small levels. And what's really intriguing here, so the first time, without any fossil at all, DNA evidence is predicting another hominin which must exist here, which interbred with the Denisovans. So people have got to go out and look for that. This will be the future of paleoanthropology. But if you're of African origin and heritage, you won't have any Denisovan or Neanderthal DNA. And intriguingly, Africans have the widest range of genetic variation, and all other Homo sapiens essentially fit within that pattern, which is consistent with the notion that Homo sapiens evolve in Africa and then move from Africa out throughout the rest of the world, colonizing the rest of the world. A little bit of interbreeding on the way, but very small changes in DNA. So it's been said, and it's absolutely true, that we are all Africans under the skin. And I think, this is where science moves over into some very interesting areas about equality and the way we treat each other, because it suddenly reveals that the very fine differences we like to erect between us are mostly fantasy. And there's us. But you don't need to be introduced yourselves. And here is a pretty up-to-date version of the family tree. But the thing I wanted to point out is how human evolution looks just like any evolution of any other species. In other words, you have these different radiating, running experiments all going at the same time. Some come to dead ends, some lead on to others and to evolved versions. But at any one time, I remember the fossil record we've got at the moment is pretty thin on the ground. New fossils being found all the time, but it's like a jigsaw with many of the pieces missing. But even with this level of the jigsaw, about 2 million years ago, there are at least 5 different hominids existing simultaneously. So the fact that we find ourselves as the only remaining hominid species is totally unusual. It's a complete aberration. And it's only been true since the Neanderthals went extinct, which was 27,000 years ago. That sounds like a long time, but believe me, in geology, that's nothing. That's absolutely nothing. Here's a chart of human brain development. Now, this is not sophisticated, so this is not power-to-weight ratio. This is just how big your engine is. But you can see that it produces a nice kind of curve. But the really important thing is what's going on in here. You can have a 2-litre engine which has less power than a 1-litre engine, depending on how the internal structure of the engine works. And Stephen Mython, who's an archaeologist at Reading University, came up with this theory of modal intelligence. Because we have to explain how it was that our precursors were very, very clever at surviving and thriving in very harsh conditions, which you and I would find almost impossible. They have to have a really good understanding of how to work technology to create stone tools, etc. They have to understand natural history. They need to know what to eat, how to eat it, where to find it. And his suggestion was that a bit like a cathedral with lots of different chapels and rooms, the mind of our early precursors was kind of separate modal intelligences which weren't connected. The easiest explanation of this is if you drive a car, at some point or another, I guarantee you'll have driven somewhere and not known how you got there. That's using modal intelligence. So you have the ability, you know what to do and you're reacting, but in one sense you're not connecting that bit of thinking with other bits of thinking. He thinks what happened, although it's still not really understood exactly how, is that the walls of those chapels came down, and in Homo sapiens we connected up those different sorts of intelligences so we could put them together and think in a much more fluid and creative kind of way. And the evidence for the emergence of this new brain and for symbolic thought is plentiful. So we've got cave painting. This is a bit of red ochre from Lombus Cave up here in South Africa. That's about 70,000 years ago. That's about the earliest evidence at the moment for kind of deliberate symbolic scribing. These are thought to be early musical instruments. These Venus figures turn up all over Europe about 25,000 years ago. These beautifully carved harpoons, the earliest of those goes back about 90,000 years. And for my purpose with religion, you get the onset of clearly deliberate burials with all kinds of grave goods, and here presumably these ivory beads, which each take hours to produce, would have been sewn to clothing which is now gone. But you can see what kind of effort has gone on. This tells us not only about the care taken in death, but about a new understanding perhaps of status and significance in life. And the key adaptation, which probably finally separates us from other hominids, although there's a bit of a debate about Neanderthals and the degree to which they could use language as we do. But once you have the ability to use language, which of course is a totally symbolic system, there's no relationship between the word dog and the furry animal. That's entirely arbitrary. It's why learning other languages is a pain. But once you've got it, it gives you access to a virtual world. When you can use language, you can describe things from the deep past, and you can think about things that might happen in the future. You end up with a notion of self and awareness of your own mortality through that kind of thinking. You can engage in self-conscious thought and reasoning. Sometimes, of course, it's possible to think without words, and we seem to be able to arrive at conclusions without a string of thought. But to kind of process that and engage in it, make sense of it, it's very hard to think without words. It's as hard to think without words as it is to do maths without numbers. Words, language enables us to construct models of the social and material world. So language is essential to science, and language lies at the root of our religious sensibility, so we can conceive of an alternative world. We can ask ultimate questions. We can think about the person of God. So it has to do with religion, and it's our most distinctive adaptation. So within the realm of science, within the realm of paleoanthropology, what do they make of religion? Because the interesting thing is, here people are engaged in the scientific method, and they come up against evidence for the emergence of religion. And the emergence of religion just when modern human thinking starts to begin. So it happens, evidence for religious activity, like deliberate burial of the dead with grave goods, emerges around the same time as art, a whole range of different phenomena. Well, if we go to somebody I find who's a very good balanced thinker, Chris Stringer, who's at the Natural History Museum in London, it's often on the TV. What can we say about religion according to this? Well, that it emerged about 100,000 years ago, that Darwin thought it was the product of a theory of mind. That is, that when I'm looking at you, I'm able to imagine what it is you're thinking about me or about other things. So I can project my notion of how I think onto you and attribute you with other minds. And if you put that together with a strong desire to find cause and effect, Darwin thought those two things coming together were what gave you a notion of God. An explanation for maybe sudden disease, there must be a reason why X has died, put together with a theory of mind, kind of projected onto the furthest horizon. Some people think that religion came about because we were able to remember our dreams, or because we could induce trance-like states like shaman, or because we took hallucinogens. But by all those means, you become aware of a world which is other than the world you're occupying now. A minority is a tiny minority. See it as pathological, as the opiate of the people, and the sooner we could rid ourselves of religion, the better. But the interesting thing is that religion has persisted. Why has it persisted? Why does it mark out the Homo sapiens? Vast majority of Homo sapiens around the globe, of course, engage in some kind of religious belief and practice. Well, paleoanthropologists think because it's deep-seated, pre-programmed and inherited, that it's a bit like our ability to pick up languages. We seem to have a predisposition for learning a language at a certain point, and that same predisposition we have for thinking religiously. Or because it discourages harmful behaviours, particular sorts of sexual relationship perhaps. Or because it's a source of transmitting knowledge via myths and stories, like the dreamtime of the Aborigines of Australia. Perhaps it has a unifying effect on society. Perhaps it's an antidote to depression, pessimism and anxiety. which handicap health and longevity. But all those explanations for religion, of course, are inherently reductionist, which I put in red. That is, they seek to explain and understand the existence of the religious sensibility, which paleoanthropology has itself discerned, on the basis of that which is not itself religious. Should we be annoyed by that? Should we be annoyed by their reductionist explanations? Of course not, because it's a product of the scientific methodology we employed and examined earlier. Science asks and is very good at asking certain sorts of questions. But as we saw, there are other kinds of questions which it can't get to. And it's very unfair to expect a paleoanthropologist who's writing as a scientist to move beyond the scientific method. So of course, they will demonstrate what looks like a reductionist explanation, but that doesn't mean that the things that they say are any the less true or worthy of examination. I mean, God may or may not exist, but religion does hold people together. Religion holds people together even if God exists or God doesn't exist. We just have to understand the limits of what's being said. I'm coming for my last little bit now, which is about the relations between science and religion. I'll do this very quickly. Religion has responded in some very poor ways, some embarrassing ways, frankly, to the advance of science. One way to do it is to say, scientists are really good at understanding the world out there, so we'll retreat. We'll just talk about the inner world of human thought, and we'll leave scientists to worry about the rest. I think that's a very poor response. Sometimes, despite all the evidence, religious traditions will still assert old theological explanations as true. I've picked here creationism. I was a geologist before I became a Christian, and my first encounter with Christians was in Wales, and Welsh Christian unions were at that time very influenced by American creationism. So the first day I turned up and thought I was one of you, I said, turned out I wasn't, because I asked awkward questions about the flood and things like that. There is a kind of heroism that the more you can believe something which is impossible, the greater the faith. But that's a very dangerous route, because there's no criteria for it. If you want to believe impossible things, I can give you endless impossible things to believe. I think there is an onus on religion to listen to what science says. And of course there's this old one, looking for God in the gaps that science leaves, or only in the miraculous and the spectacular. I don't think that's the only place to look for God. But God and science need not be in tension. God, if God exists, is not a member of the set of creation. That's a kind of philosophical way of saying that God is above and beyond time and space, and therefore a God who existed would be beyond direct scientific inference. It's just a kind of philosophical way it cashes out. If God exists, all else exists because of God. Therefore, in one sense, all is God's action. Thus, God can be at work and present in and through the causal nexus that science investigates, not merely the odd and the curious. And we've seen a move throughout the 19th, 20th, into the 21st century of people wanting to ask how is God or God's action to be found in what seems like the mundane chains of cause and effect. Finding God's activity in the world is a lot easier when our interpretive framework is not that of a machine, which it would have been for Newton, but when we see the world as probabilistic, even at the level of matter. I've got time to talk about the double slit experiment with electrons, but it's just incredible. We don't know what matter is. We have an interpretive framework which we use and apply and seems to work, but as soon as you get down to small levels, that breaks down totally. In if there's room for human freedom, then there's room for God's action. If I move my phone from here to here, as far as I know, I've not broken any rule of science, but the only explanation for why the phone has gone from there to there would involve something to do with my will and desire. If I can act with freedom in and through the causal nexus, so, at least in theory, could God. If God is the creator, then what science describes about the world with due account for its provisionality is relevant to theology, and theology must take account of it and respond to it. That can be a hard position to occupy, because it means that inevitably it'll bring you into some conflict with some of the inherited notions of a religious tradition. Science operates in a system of assumed values, political and economic, so it desperately requires a perspective and vocabulary to challenge it. Science, as I pointed out, science can't decide whether it's ethical to do certain sorts of experiments on human embryos. It needs to be in dialogue with other kinds of traditions and ways of thinking to make those sorts of decisions. So it's essential that science doesn't operate as if it were the only system of legitimate rational thought. Belief in God, and thus that the world was rational and orderly, helped inspire the scientific method. That seems to have been true in where Islam, Christianity were present. I don't know enough about other traditions to know how they might have impinged upon the scientific method. And I think religion and science meet in wonder. I think that's the kind of garden they share. If they live in different houses, then at lunchtime, as it were, they come out and meet on a bench in Wonderland to eat their sandwiches. So, summary, very quickly. Who are we? We're the product of a 4 billion year evolutionary history marked by chance events, yet emerging within an underlying structure of life. That's massively controversial. I'm siding with Simon Conway Morris against Stephen Jay Gould. Ask me about that later. We are creatures of symbol, art and religion, who by the use of language can conceive of alternative worlds. If we've learned anything, we've learned that we should not take the present and its structures and its understanding as ultimate. There are always other ways of conceiving things. And a posh way of saying that is beware of ideology. We are creatures with an inherent religious sensibility, open at least to the existence of God. Though, of course, not all people find that plausible or possible. And we are creatures of wonder, curiosity and imagination, open to the new. I think that's who we are. And finally, I leave you with some English faces. Who's this chap? Been on the news? Cheddar Man, yeah. So this, the oldest complete skeleton in Britain from Cheddar Gorge, dating 10,000 years ago, blue-eyed and dark-skinned. Who's this chap in the mirror? Neanderthal, who occupied southern Britain, perhaps as north as Chester. And we know from the genome of Neanderthals, some had red hair and pale skin. And here's a contemporary looking in the mirror. Perhaps he's got more than 2% Neanderthal and is feeling a kind of sense of affection. But I'll leave us with I think that's just, hopefully that makes you wonder and think and ponder, and that's the point. There we are.